All right, let's start going with today's class. First things first, I thought there was going to be someone here to chat with us for a couple minutes about the Tufts engineering mentoring business, which is basically if you're actually you don't even have to be an engineering major, but if you there is a Tufts engineering mentoring system at Tufts that gives mentors and provides mentors to underclassmen and provides upperclassmen the option to do mentoring for underclassmen. In other words, how do you get through an engineering curriculum or a technical curriculum? And he was going to talk about that. So he came earlier. I didn't know, maybe he didn't know that we had this class. But the one thing I wanted to pass on, I put on Piazza a link to a very short, I think it's short, survey about the Tufts mentoring engineering mentoring system. So if you get a chance, because I know you're not busy this week, could you if you get the chance, take a couple minutes to fill that out if you're interested in possibly being or having a mentor in the department, or in the school. Okay, here's what we're going to do today. So we can certainly talk. I will entertain any questions about the project. Hopefully by now you know that the project is the due date is actually postponed until next Tuesday. If you haven't figured that out yet, well, happy birthday. I hope it's okay to that you've got a few extra days. And still, if you need extra help between now and then, there's office hours today and tomorrow, and TAs should be around and so forth. So we'll go with that. The big thing I wanted to talk about today, I mentioned it to you guys. I wanted to talk about kind of things you might need to do, might need to know to prepare for Comp 40. Many of you are not taking Comp 40, so if you have other things you need to do, you are certainly welcome to leave, and I will not say, I will not be upset if you want to take off. But I do think you'll find some of it interesting anyway, regardless. But if you're not taking Comp 40 and never plan on taking it, then you can say, well, see ya. That's fine with me. But you certainly can. I urge you to stay if you don't have anything really pressing to go do right now. So let's see. Before we get going on the Comp 40 stuff, anybody have any questions pertaining to the project? Homework 5. Yes, James.
What's the best way to insert at the end of a vector?
The best way to insert at the end of the vector? Anybody? Push back. That will do it exactly right at the end. Push back. Okay. And then that's the fastest as well, because it doesn't need to do any moving of data. Yeah. Try not to insert if you can help it, because you have to move data. Good. Other questions? Yes, Nathan. Yeah. Oh, very good question. The question is about are we worrying about the memory size of the program? To a first order approximation, no. I think there's plenty of memory on the systems that you will be okay. If your program is taking like 25 or 35 gigabytes of memory, it's either going to page out the memory to disk and then it's going to slow way down, or it will run out of memory because other people are using the system. So no, you don't have to worry about it because you probably will be okay. If you're finding really weird seg faults when it's working, sometimes doesn't work on other data, that may be an indication of a memory problem. How do you check it? There's a program called /usr/bin/time. And we've used time before. This is a slightly different version. If you use that and then the -v flag for it, and it's on Piazza. I put a thing on Piazza on that. It will give you the listing of how long it takes. You can also use valgrind. The problem with valgrind is trying to do valgrind. Valgrind slows your program down so much that it could take hours to get through your program just to read in the data for the big data set. So it's not going to help you much. The time one does not take much overhead at all. So take a look at that. The one caveat is it will give you a maximum memory. I think it's called, what's it called? I forget. It says something about in-memory size or something like that. It's 4 times too big. Divide it by 4. It's I don't know why. There's a bug in the program. And it's open source, so I should just go fix it. But it's a bug in the Linux program. But it's just 4 times. So if it says 12 gigabytes of memory, you're really only using about 3. Okay.
Functions. I know we're only supposed to have functions that are 30 lines. Does that mean it's 30 lines of code, or are we allowed to have spaces for readability and comments?
Yeah, that's a good question. There'd be 30 lines of code. It should be 30 lines total. That's what the programs check for. Now, somebody asked that earlier, and Bruce happened to be here, and he's like, it should be absolutely 30, blah, blah, blah. And I get that. The problem with making it, the problem with functions when they get too big is obviously there's too much going on, and if you try to debug it, you're not going to be able to figure it out. So if you break it into multiple functions, you can generally figure out where your bugs are easier. So that's the theoretical reason about why we make you do that. And don't go crunching your code up with comments like scrunched in to make it non-readable, because you'll lose points there too. I mean, the maximum you'll lose is like 1 or 2 points for being over 31 lines, like total for your program. So I made this comment to the other class. If you're a couple lines over, I'm probably not going to worry too much about it. Like I'll give you points back if a grader says, oh, you're off by, well, exactly. But don't make it a habit. I guess that's my comment there. Good. Other questions, Susie? Yeah, good. That was going to be my next topic, in-person grading. So some of you probably have actually already done an in-person grading with either a TA or Bruce. Bruce kind of got on it immediately. In the next day or two, you should see an email trying to schedule you guys. It'll be basically go to this form, fill it out, and find a time. And 20 minutes out of your time, it shouldn't be too bad. It shouldn't be too bad. Wait for the email, yeah. Or you can email your TA, but I mean, or your lab TA if you want, but that's me, so you're not going to hear anything from me. No, it's not me, I don't think. Anyway, it might be for yours, I'm not sure. But anyway, the point is just wait a couple days, and hopefully it'll be all figured out by tomorrow, and then we'll get it out of the way should be before reading period. I'd like to get it done before reading period because that's kind of sacred. Lydia.
What exactly, what does it mean if you run Valgrind and it makes things work that didn't? Does Valgrind do that sometimes?
Does Valgrind make things work that didn't? It probably means there's a bug somewhere, because what happens is a lot of the times if you have a piece of memory that's that you expect to be there, and then let's say you didn't use new properly and it supposedly goes away. Well, it might not go away. That's kind of up to the operating system. So it still could work, but then Valgrind might do, and then it might not sometimes. Then sometimes Valgrind has a different section of memory, and so no, that probably means there's a problem with your program. If you're getting fixes with Valgrind, that's probably that. Yeah. There was one other thing I was going to say. Shoot, what was it? I forgot. I'll think about it. Any other questions? Yes.
There's an arrow about a warning about a K8.
Oh yeah. Okay. So there's a warning about this K8, and somebody the other day said, "Oh, I took out all the K8s and it broke." There's one. It says 2 specific lines in the warnings. If you want, comment those lines out, or just remove those 2 lines. Don't remove every instance of K8, but there's 2 lines that it says. If you want to remove those, that's fine.
Yeah, but then I got another warning about K8 not declared.
Right, you probably removed the wrong one. There's like 4 instances of K8. 2 are necessary, 2 are not. The ones that aren't, it will give the first warning about. So those are the ones you need to remove.
Another question?
Yeah.
If the keyword we're going to search is the first word in the lyrics,
Yes.
do we print 10 words after that?
No, just 5. If the first word is the lyric, if the first word of the song is the lyric, is the one you're searching for, just print that word and then the next 5 words after that. Good. We had another one up here, and then Yuval, and then yeah.
I got for that. I get a warning from the get alpha function that you provided saying there's a change in assignment or something. Should we worry about that because it wasn't code that we wrote?
You shouldn't worry about it, but I'm curious why you got it, because it wasn't. I didn't get that. Did other people get the same warning? No. Something else.
It's coming from W sign.
No, right. I just don't know why I don't know why it's happening for you. If you want, stop by and we'll take a look. Okay. It shouldn't be. It should be an easy fix. Henry.
Could you explain the relationship between the load factor and the load max?
Yes, good question. The load factor is simply the number, if you're talking about a hash table, the load factor is the number of items in your table. How many things you've put in there. That's the load, what did I say? No, sorry. The load factor is the number of items divided by the capacity. So you've put a certain number of items in there, right? If that's 5 and your capacity is 10, then your load factor is 0.5. Right? You should probably try to keep it around 0.5. So if it gets to be a little bigger than 0.5, then rehash, expand. Yeah, that's the difference there. First, we'll go up to Sam.
So in the project description,
Yeah.
you print out the context. The first word of each line is capitalized, so you can tell where it's located at the end of the line or beginning or whatever.
Not necessarily. I don't think that's.
In your project.
No, I didn't account for that. I don't think you need to account for that. I don't think you can, because there could be words.
It just allows you to tell like where the word is in the line, but alpha only converts everything to lowercase.
Right. I'm just not sure that that's true for, because there are capitalized words inside the songs too.
Okay. But if you're printing the context and you're using alpha only, wouldn't everything be lowercase?
Yes, but so keep in mind, there's a way to do this. So your lyrics have, some say I blah blah blah, right? Let's say that's your lyrics, right? And you're looking for some, right? Well, what you can do is you can pull some out, and then you can do alpha alpha only on your word that you just pulled out to do the comparison. But then you print this out. So in the lyrics, you store this. When you're comparing it to the word that you're searching for, you take this out, and then you do alpha only on it, then do the comparison, but then print the original. That make sense? Yeah, yeah. And if you don't do it that way, you're not going to lose a zillion points. Let me put it that way. I mean, these are like little things that, yeah, you should think about, but that's not going to screw up your algorithm. At least it shouldn't. AJ, you had a question.
Do we have to worry about from the load factor converting from or using like operations on ins and unsigned?
Do we have to? Oh, in the load factor, do you need to worry about unsigned and ins? No, not really. I mean, yes and no. I mean, if your table is int sized, and we're not going to have more than 4 billion entries in it, it should be fine. Or actually 2 billion because it's an assigned int. You should be fine. But when you're doing your load factor, if you've got the number, let's say your variable is n and little n for the number of items in the table, and big N for the table capacity, or just capacity, right? If you do n divided by capacity, right, that will always give you 0. If that's an integer and that's an integer, because this is less than this, and this is integer math, and integer math will truncate down to 0. What you need to do is you need to cast one of these. Generally, it doesn't really matter, but if you say float and then the capacity, right, what that'll do is that'll say n divided by, it'll say, oh, capacity is now a floating point variable. Oh, OK, I can make it a floating point answer. That's the one thing you have to be careful about. So I've seen a few people do that. Forget to make their integer math work out properly, okay, with actual floating point math, because you're doing a floating point number. Yeah, Allie?
Can you just declare, like when you declare those private variables, can you just call them floats instead of ints?
You probably shouldn't call them a float, because the capacity is an integer. And when you're doing comparisons with integers or with floats, you remember how you never know exactly what the comparisons against integers isn't going to work. So if you're comparing am I at my capacity or something like that, and you also can't do modulus on a capacity that's a floating point value. That doesn't mean anything. So you have to do those as integers.
Okay, so
Yep.
then in order to, is that the syntax for like turning capacity into a float?
Yes, this is called casting, which means you will take it, and capacity will now be turned from an integer into a float, which is a legitimate thing to do. OK, Margaret?
Sorry, just to clarify this. So if you have 2 integers and you're trying to calculate the load value,
Yeah,
the load factor is what you need to do.
Yes, because if you have 2 integers and you said, if you had 5 items in your table and you were dividing it by 10 items capacity, that would be 0 in integer math, because it's 0.5, but that gets truncated to 0. So you have to cast one of them to a float, which just means put a parentheses like this, float, like that, in front of it. That's all. The ideal load factor, try to keep it under about 0.5. I tried 0.8, and that was too slow for mine. But, Lydia, you had a question?
What's the deal with the member functions of vectors that are like the element access? Because it says they return a reference, but they don't behave like pointers. They behave like they attempt to return the element itself.
Oh, I'm not exactly sure. When you say they return a reference, if it's a reference, you can use it as if it's a regular variable. So don't worry about that. Don't worry about doing anything different. You should be able to use it as a regular variable. Yeah, good. Owen?
For the same problem, shouldn't you just divide, put capacity in the numerator and n in the denominator, as long as it's bigger than 2?
You could do that, sure. Yeah, you could do that. You could flip it and make your load factor be a integer. Yeah, if you wanted to do that, sure. Good. Be kind of the inverse load factor, but yeah. Other questions? Okay. All right. So here's what we're going to do. We're going to start going into the Comp 40 stuff. Like I said, if you're like, I'm not doing Comp 40, I'm never going to do it, and I don't want to sit through this, that's fine. I'm not going to be upset. I am going to write your name down, but no, I'm just kidding. But anyway, we'll talk about this. So here's what we're going to do. I'm going to go over just a brief little thing about kind of Comp 40 in general. And then we're going to talk about C and C++ differences. And then we're going to dig in just a little bit into the actual memory system and see how some of this C code and pointers actually what it does in memory. Because there's a few key things that if you don't take into Comp 40, you'll have to figure them out when you get in there, and you might as well do it ahead of time so you start a little bit ahead. Okay? All right. First things first, what's Comp 40 all about? Well, this is straight from the web page. You will turn the corner from introductory programming to programming as a professional. All right, what does that mean? Well, right now, even though we're trying to get you right now with this song search thing, kind of on that cusp of doing a pretty intense, like lots of thought kind of problem, right? But it's not going to be quite the same level as if you were doing a professional program where you can't have any errors, for instance. Okay? You always have bugs in your code. I mean, bugs are like in almost everybody's code. The only people that get away with like very, very, very few bugs are people who send things into space, especially people who send people into space, like NASA, right? Like when NASA writes their code, like they have one person write it. I think their average programmer at NASA writes about, I think they said something like 5 or 6 lines of code a day. Like that's how much code they write 5 or 6 lines of code. It's all to spec and it's all perfect. And then 6 other people look at their code before it gets submitted into the actual program. And then they have a whole other team that tries to break the code. And it's like super intense, right? Well, while Comp 40 is not quite like that, there are some rules in there that, for instance, if you submit your program and they test it and they figure out how to make your program segfault, you get a 0 for the assignment, right? That's the end of it. They just say if your program had a problem that would enable it to segfault, well, you get a 0, right? And I don't necessarily agree with that for some reasons, but that's their policy, right? So you kind of have to be a little more intense about making your programs work right. All right, fair enough. The actual meat of the course is the structure of modern computers via all this programming that you're going to be doing, right? You have to know how hardware works, operating system works, compilers to a little bit extent, language runtimes, like how the actual computer makes your program run, what it's doing under the covers. It's all about like looking under the covers and saying what's going on under there and how's your computer actually working, which I think is kind of fascinating, right? But it's also kind of intense because there's a lot going on down there, and it's not trivial stuff. Okay? You will write a lot of code, and you'll write a lot of C code versus the C++ code that we've been doing, right? It's lower level, and we'll get into the details of that in a minute. You'll also write some assembly language code, which is really low level, right? And I think I showed you one program that was assembly code, and I said, oh, this is so ugly, you'd never want to do this. Well, you're going to do some of it, right? But that's OK. It's actually very beautiful in many ways, but it's also low level stuff. You're going to have programming partners in Comp 40, which means that you will have a partner and you swap partners every time, right? So you'll meet a ton of people, and you'll be able to work with a lot of different people. And the good news is 2 heads are better than 1 when it comes to this intense stuff, right? This pair programming stuff is actually pretty good when it comes down to it. It's kind of provably a good way to actually do programs. And you can lament over things with your partner as you're sitting in Halligan at 2:30 in the morning too, right? And then you also have to do design documents. The design document I had you do was like this long versus like you're going to have to put some beefy stuff together. And why do you do that? So that you don't start on the wrong foot, or so that you have an idea of what you're doing. It's common sense kind of stuff. And there's going to be a lot of reading to get up to speed. What do I mean by that? Well, let me see. I'll jump to this slide first. The most important slide that I'm going to show you is actually the reference. You should go to this web page. It's the Comp 40 webpage, and it has a reference section, and start doing the readings and start doing look at the coding standards and like some of this other stuff. The whirlwind tour of C is great too, okay? It's like stuff that over the summer you probably want to look at. Why? Because you want to be ready for this stuff. And and I think by doing that you'll be in good shape. the coarse coding standards, like we were just talking about, hey, do you need to make your functions 31 lines? Yes. Well, in Comp 40, it's not. It's you have to have 8 spaces for tabs. Like your tab has to be 8 spaces. You have to put the function calls in the right. You have to bracket everything correctly, and it's like very detailed stuff. Why is it detailed? It's all about attention to detail because you want to make it. You want to make it like perfect, right? So that's the way. But anyway, this is the like super duper important slide there. I'll flip back to it for a sec. Okay, so a bunch of reading to get up to speed. Do it over the summer, and you'll probably be good to go. One of my suggestions, and I think I've told all my people who I've talked to about Comp 40, do some programming in C over the summer. The song search, if you get your song search working in C++, go rewrite it in C over the summer, and you will run into a whole bunch of little things that you go, oh, I didn't know I had to do that. Oh, I didn't know how to do that. Oh, that's interesting. I can do it this way. So you'll get that. You'll get up to speed a little bit more. Okay? All right. So we were talking about C. What is C all about? Well, first of all, C is a relatively, well, not an old language, but late 60s, early 70s, it was developed at AT&T Bell Labs, one of the premier research labs in the country, at least at that point. And this guy named Dennis Ritchie, he's won lots and lots of awards for this. C is very closely tied into the Unix system. All right, the system we use is very closely tied in. Why? Because C is a systems programming language, and Unix is a system that it was designed to work with. So very close-knit. C is very close to metal. Again, it's low level enough that you can do all the little things that you might do in assembly language and make it really fast. C++ is pretty good too, but not quite to the same extent. Okay, here's another little couple slides on C. This is a programming languages list of what the most used programming language is based on this company's research is. C is the most widely used and has been for many years. It switches with Java every so often, which might mean you want to learn Java at some point too, because that's kind of an important one. This one blows me away. Anybody have an iPhone? Objective-C is what you use to program iPhones. The fact that Objective-C is more widely used right now than C++ is amazing, because because 10 years ago, nobody, like 0 people were programming in Objective-C. I mean, it was like, it existed, but it was such a small amount. I'll show you another one in a sec. There's some other languages on here. Python's one, the big one. JavaScript using the web. Not as many, I wouldn't think as many people do Visual Basic. It's probably because a lot of companies still use it for whatever reason. But there's C++ is on there, going down, by the way. Notice it keeps dropping because not really the best language in the world. Okay. Why am I teaching you C++? Yeah, well, OK, yeah, good question. Fair question. We're teaching C++. It would not have been my first language to teach you. Let me start by saying that. C++ is some of the things that you have to do in C, we don't want to make you do in C++, but we want you to be ready for Comp 40. So it's kind of the mix that you have to get to do that. We could have taught you Java. You wouldn't know enough to do C. Structure's a little different. It's a little more verbose. We could teach you Python. I'd rather teach you Python, but then you wouldn't know how to do C. We could teach you Lisp or Scheme, but then you might not get a job. What's that? Yeah, I know. But in a couple years, when you're looking for a job, if you don't know a function, or if you don't know an imperative language, you're going to be in trouble trying to find jobs. I mean, that's the only issue there. But yeah, so there's lots of reasons. But C++ is an interesting mix. But that's that. Here's another graph. The top line here is C. You notice it dropped a little bit, but it's always been near the top. Java kind of eclipsed it for a little while there. C++, going down a little. Objective-C for the iPhone. Look, it's like 0, 0, 0, 0. Oh, iPhone. Whoop. Right? So it's that one's like super duper important because Apple, like the iPad and iPhone and whatever. Okay? So that's kind of where C came from. All right, what do you need? This we already talked about. Go to this web page like over the summer. If they take it down, I'll make them put it back up. All right? Going from C to C++. Let's talk about a couple little details here. Okay? A couple little details. First of all, they're very similar. They have similar feel. C++ is based on C, so that's why it feels very similar. It does have the same types of things, types you're used to: int, chars, floats, doubles, etc. You can use structs. It does not have classes, but it does have structs. You can do array indexing using brackets. You don't do that quite as often in C. We'll see why in a few minutes, or we'll see an example of what you do instead. Function declarations are the same. You put void, you put int, you put whatever, right? You do have .h and .c files now. Okay, you keep them separate generally. And the flow is the same. You have while loops, if loops, for loops, all the same. Okay, so it will be very familiar in that sense. Here's some of the things that are different. Strings. There is no string type. Does not exist. No type of string. Strings are simply null terminated arrays of characters. What does that mean? Character, 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 0. And not the character 0, like the actual null character 0. Right? That's all a string is. And you have to know, you have to be able to use those. And you have to be very careful with them. We'll talk about those a little bit more in a second. Okay? No classes, no objects, no constructors, destructors. There doesn't exist in C. Why? Because there are no objects. Everything's a function, or you have variables that you declare. Most of the times it's pointers. Memory management is different. There is no more new keyword. You don't use new. You use this thing called malik, memory allocation. You can do that in C++ too, but most of the time we use new. You can do this thing malik. Malik, you provide a size to it in the number of bytes that you want. So let's say I want 10 integers, and integers happen to be 4 bytes long. Well, I have to say to malik, give me 40 bytes of space for my integers. All right? And malik says, sure, here's 40 bytes. And in fact, malik doesn't even care what type of pointer you are. It says, you need 40 bytes, here's 40 bytes. That's all it cares about. Okay? You have to know how to ask that. How do you know how to ask how much? Well, you use this thing called size of, which we will go into in a sec. That gives you how big an integer is. And it does depend on platforms you use too. Okay? To free memory, you use free. It's very similar to delete in a lot of ways. It's you just give it the pointer and it says, oh, I know it needs to be deleted. Foop, and it deletes it. You can't pass by reference in C. You do pass everything by value. You can pass structs and things, and you can pass pointers. But that's it. There is no bool type. C does not have a Boolean type. Doesn't exist. If you want to compare two things, if it's false, you'll get a 0 back. If it's true, you will generally get a 1 back. But sometimes you get anything but 0, depending on what functions you're using. But that's the way C defines it. It says 0 is false. Everything else is true. That's what they say. Okay? No Boolean type. You can define a Boolean type, but it's not built into the language like it is in C++. OK. So back to the character strings for a minute. Null terminated character arrays. No string class. No string class. How many times do I say that, right? You can't use your strings. You got to do it slightly differently. You have to be careful that you have enough space to put those strings. The nice thing about C++ is you declare a string and you keep putting characters into it as long as you want, and it'll keep expanding. It's just a dynamic array. In C++ or in C, if you have only a certain amount of space, you better make sure you don't try to put too much stuff in that, because it will overrun this and cause what we call a buffer overflow. And that actually can crash your program. Okay? And so you need to do things like use this function called fgets, which says, hey, I'm only going to allow 256 characters into my string. Okay? And if you put a new line, that character counts. And the 0 counts at the end. So you got to be careful with these things, right? Okay? And by the way, these are all on the slides. You can go back and look at these at your leisure, but just wanted to throw them up here so that you can have them for a later reference if you want. Okay? This is a big, busy slide, but all it says is there are string functions. There's a string library. You can do things like string compare, compares two strings. It returns weird values sometimes. It returns if S1 is less than S2, it gives you a negative value, any negative value, whatever it happens to want to do. It'll give you 0 if they're the same and positive if S1 is greater than S2. Okay? That's their way of doing a ternary comparison, less than, greater than, or equal. String cat, stir cat concatenates two strings together. You have to be really careful. If you have a buffer that holds 20 characters and you have two strings that are 10 and 15 and you try to stick them in that 20, you will overrun that buffer, and C does not care. C's like, your problem, not mine. Right? C doesn't care. It won't give you a warning. It might give you a warning if you're lucky, but it probably won't. Like the compiler might, but it probably won't. String length, etc. So you can use these functions, but they are definitely lower level than the ones you use in C++. Okay? Questions on strings characters? Yes, Madhvi.
Do like charge
Yeah, you can also do a char. Chars are just integers. They're actually just integers that are generally, instead of 4 bytes, they're either 1 byte or 2 bytes or something like that. But yeah, they are just integers. You can't do all the functions. These are the ones you get generally. Compare, concatenate, copy, length. That's about it. Can't do all the other things. And it's all based on the characters inside those strings, terminated by a null. Remember that bonus I put on the midterm that had the weird pointer arithmetic? Like that's using the idea that strings are nulls at the end. So it's interesting stuff. It's just a little more low level than you might expect. Okay? All right, structures are slightly different. Structs are generally the same, except that you can't put functions in your struct for C. Not the same way anyway. You can't really do that. In C, you also have to say, remember in C++, you can say struct and then your structure, and then you just say the name of your structure and then the variable. Well, in C, you have to put this little struct before it. So a lot of times you will see this. You will do a type definition called struct name, your structure, and then you call it that, and this is what you use. It's a way of getting around that weird rule. But C++ actually made it better. Go figure. Okay? No, don't worry about this. The first time you do it, it'll complain at you, and you'll say, oh, I remember something about that. Then you go back to this slide and figure it out. Okay? All right, some other things that are the same, but you might not have talked about yet. For instance, C++ and C have these things called void pointers. What that means is, I don't know what I'm going to point at. I'm going to point at something, but I don't know what yet. Right? Malik is a very good example. Malik says, I'll give you a pointer to some memory. What kind of pointer you are, I don't really care. You figure it out. Right? If you're an integer pointer, or if you're a long pointer, or a float pointer, or a struct pointer, just the bytes. Remember, all it cares about is how many bytes you want. So that's that. You can cast variables. That's this stuff I was talking about, where you put parentheses around something, and you say, hey, here's a float, or I have an integer, let's say, and I'm making it a float because I know what I'm doing. It's all saying, trust me, compiler, I know what I'm doing, so it doesn't yell at you. Okay? Pointer arithmetic, which we'll talk about in a few minutes, is used more often than bracket notation for array indexes. We'll see why in a minute. You can use them interchangeably, but you use pointer arithmetic more often, as it turns out. You can use the double slash for comments. They aren't going to let you in comp40. They make you use these slash star and star slash block comments. Why? I think they think it makes cleaner code. I'm not sure I necessarily agree, but they believe that. So that's the way it goes. Let's talk more about these things. In particular, let's talk about malloc and free a little bit more, and size of. Malloc, it's just like new. You get stuff from the heap, right? You pass the size of bytes. Size of int gives you the size of an integer. On our machine, it gives you 4. 32 bits worth. Remember, a byte is 8 bits. So 4 of those are 32 bits worth. Computers generally are built these days to look at bytes at a time, not individual bits at a time. At the very lowest level, they're ones and zeros. But addressing, in other words, if you have an address 1 is 8 away from address 2, 8 bits away. It's 1 byte away from address 3, which is 1 byte away from address 4. Why do they do that? It just makes it a little faster. In fact, it makes it much faster, but they do it that way. OK, so that's how size of works. We'll go into some details here. If you want to, yeah, Allie.
When you said address, you meant of like in an array? Or what?
Yes, and I'll actually show you that in a few minutes. But so you have the memory, right? You have memory, and you can say, hey, I want to go to memory location 1. Well, that's here, right? Memory location 2 is 1 byte away. Memory location 3 is another byte away, not another bit away like it could be. If you're just doing ones and zeros, you could say, go every bit, right? But you don't. You do it 1 byte at a time. Why? Because it's easier for the computer to. It ends up being easier in the. Well, just faster in general. I mean, that's the way. And we think about numbers. You rarely deal with just ones and zeros in real life, so they make them bigger because of that. It was a design decision, but it was a smart design decision because it makes things a lot faster.
When you say like memory location 1, memory location 2, is that like how many memory locations are there? Or is it like memory location within a certain structure? Like what is that?
Do you know how much memory your computer has?
I know how much my phone might have.
Okay, so your phone has like 32 gigabytes, right? That's 32 billion bytes of data, right? Each one of those bytes is individually addressable. Now, there's lots of other things you need to talk about when you get into the details of that. But that basically means that 32 billion places you can go and say, here's a byte of memory. That's what it means, okay? And so you can address it in terms of the total amount one at a time. But it's one at a time in terms of bytes, not bits. That's all. Okay? If you have more questions about that, let me know. But the whole point is you ask for these things in bytes, and it goes. And I'll show you a memory diagram in a minute, and you'll see. OK, if you want 10 integers from the heap, you say, I want an int pointer with the star. And then you malloc it. And you say, I need to cast this because malloc has no idea what type I'm going to go become, what it's going to return to. I cast it as an int pointer, and I say, give me the size of int times 10, which would mean 40 bytes worth, because the size of an int is 4. All right? If you run out of memory, malloc returns null. Remember when I said that if your program segfaults, you'll get a 0 for some assignments in Comp 40? Well, this is the thing you need to check. If I did this, and somebody who was grading it said, oh, well, what if I fake out the system and make it look like there's no memory? This would return null, and then my program would crash. And that would be bad. Right? So you need to check this. I don't check it here just for simplicity. But you need to do things like that. Okay? All right? Free just says, up, I don't need it anymore. Goodbye. Just like delete. Okay? All right. So let's see. Here we go. OK. So here's our first little C program. It's a little more intense than your normal hello world, but that's OK. I want an array of 10 integers. Int pointer, 10, make it size of int times 10. And then I'm going to do this. I'm going to say a loop, 0 to 10, star int pointer plus I equals I times 10. What is that line doing? Susie? Yeah, instead of saying this, instead of saying int pointer I plus, oops, sorry, I time, no, I, thank you, I equals I times 10. Instead of saying that, you are saying it like this. And you're saying, do int pointer plus some amount, point to whatever that's pointing to gets I times 10. That's what it's saying, OK? So it's counting up by tens and sticking them in those locations. Nice. That's called pointer arithmetic. Okay? And it's kind of interesting how that actually works. And then you go here and you say, for I equals 0, I is less than 5, I plus plus, printf, right? And then this kind of weirdness in here. And then some other weirdness. And then we're going to ask what this prints out. Well, the other thing that C does not have is C out, or C in for that matter. It's all, you do C outs with printf. You do a similar thing where you print out to the screen with printf. And what it takes is a string with some formatting in there. And then it takes a bunch of other arguments, and it places those arguments in the place of the format string with the format that you ask for. Let me show you what I mean. Let's take a little detour into printf land. Okay? Here's what printf does. It says, let's do the example here. I equals 22. Printf, this is I colon %d backslash n. %d says, give me an integer. Print out as an integer. And then it prints out I, whatever I is. I is 22. It says, this is I colon 22. Not too bad, right? It's just saying, hey, print it out. There's your print string. Okay, you need to know some of these ones. What are they? Here they are. You don't need to memorize these. You need to know a few. You need to know ones like you're probably going to use F for floats a lot. You're probably going to use S for strings, C for characters. Sometimes you will use X for hexadecimal. We'll talk about what that is in a few minutes. But a lot of these you don't need to do. But you can also do scientific notation, unsigned numbers, octal numbers, some other, I've never used N. Nothing is printed. That's a little weird. And then if you want to print a percent, you do %%, because then it says, oh, I really want to print a percent. All right, so that's what those are. let me show you some examples of them. Let's go through these ones. And again, you don't need to memorize these. Just look them up. Characters, %C. If I do this character A and then 65, which happens to be the ASCII character for uppercase A, this will print out characters : lowercase a, uppercase a. Okay? If I then do decimals, %D and then %LD means long decimal. If this was a decimal that was bigger than the regular integer. Just prints out 1977 and 650,000. The L says, hey, if printed out as if it's a long, and notice here when they define it, it was a long, which long is generally 8 bytes instead of 4. Most computers these days. Yes?
If in the first example, if instead of the second %C you put %D divided by n, would it have printed out the 65?
Yeah, well, that's a new line. But if it did %D, it would have printed 65. If you'd done %D here, it would have printed 98 or whatever. Here it is. Lowercase a is 97. Oh, I was off by 1. 97, right? So it would have printed 97 if you'd done %D for this one, because the character is just a int. Okay? All right, let's see. Proceeding with blanks, you can actually put blanks in here. 10 blanks in this case. Again, I've rarely used that. Proceeding with zeros, if you put %010, it'll do 10 zeros, I guess, or some number of zeros, I think, until you get 10 total numbers. Nice for formatting things properly. If you want to print different radices, in other words, different bases, base 10, base 16 hexadecimal, base 8, again, base 16 and 8, it prints out 100, 64 in base 10, in base 6, or 100 in base 16 is 64. 100 in base 8 is 144. Well, don't worry about those details, but you can do that. 0x64 means a hexadecimal number. Nice. Floating points. You can print floating points in lots of different ways. You get all these different floating point format strings. Normally, I just use %f, but sometimes you use %4. 4.2f would be, I think, 4 values before the decimal, 2 after, or something like that. Okay? And then exponential notation, etc. You can do, there's a little width trick to make like the width be proper. And then strings. %s, a string will print out a string. Okay? Don't worry about the details. You'll be able to see this when you do it. But now you know about printfs. No couts. OK, so let's get back to this for a sec. What's this going to print out? Figure this out. We put 10 integers in there, I times 10 each one. What is this going to print when I run this program? What's it going to print? It's going, yeah, and what are those numbers going to be based on this program, Ethan? Every other number in the array. I think it's going to be 0, 20, 40, 60. Right? Because it goes 0, 10, 20, 30, 40, and it's going to go 0. So this right here says this is more integer pointer arithmetic, right? Int pointer plus I times 2. So I go 0, 1, 2, 3, 4. So it's going to be 0, 2, 4, 6, 8. And I put 0, 10, 20, 30, 40, 50, 60, 70, 80, 90 in there. That was a lot of words. It's going to do every other one, really, when you print this out, because of the pointer arithmetic. Okay? 20, 40, 60, 80. All right. We're going to dig in a little bit more on this right now. I think it's kind of fun. Maybe not right now, but in a minute we're going to dig in a little bit more. The pointer arithmetic part is interesting here. The compiler knows that integers are 4 bytes long. So when you say int pointer plus I, and I is 1, let's say, it will say, OK, I know the integer pointer's here. 4 spaces away is the next one. That's where I'm going to say the address is. If I do int pointer plus 2, 4 more addresses away is the next one. Because the compiler knows that it's not just plus 1, it's plus 1 times how big an integer is. I'll show you that. Okay. Int is 4 bytes. And the compiler figures it out, which is kind of nice for the compiler. Right? You don't have to figure out, the compiler does. It used to be that you had to figure this stuff out. But people say, why don't we just make the computer do it? Sure. Yeah, Al.
Sorry for all the questions.
No,
but,
absolutely.
So at the top when you say alak,
Malik, yes.
Malik,
Yep.
when you say size of int, you could just do Malik 40, right? Because we know that the size of the int is 40.
Absolutely. You could do Malik 40. Here's why you don't do that. First of all, you might be using a different compiler which says, hey, my int's a different size. C does not define the size of an int. Java does, by the way. Other programming languages do, but C does not. C says, hey, whatever you want it to be, you can do that. And it's because different hardware might have a better use for an integer than to be 4 bytes. Like really small hardware that's like really simple might only have 2 bytes for an int, right? It might have 8 bytes for an int if it's a 64-bit system and they wanted to do it that way. So you don't know. You do know that you will get 10 integers worth. But unless you do this, you won't necessarily know you'll get the right amount unless you do the size of it. That's why.
And so
Portability is what they call it.
So that's not because we would ever like actually encounter a compiler that allots different amount of space for ints, but just because it's like good to get into the habit of when we're.
Oh, you absolutely might. You might get a compiler that does that. Yeah. If you're doing embedded systems, like if you're doing like little tiny computers like for robots and things, you might get an int that's only 2 bytes long. Yeah.
But like in comp40?
Not in comp40 you won't. No, it'll be the same. But you're going to want to do it that way. Yeah. Good. And they might use a different compiler on you. Who knows? I don't know. OK, ready for this? Let's look at the memory. Let's dig in a little. This is where it gets, I think, a little bit fun. OK. All right, let's look under the covers a little bit. What you can do, if you're using an IDE like Xcode on your Mac or something, you can say, hey, stop the program right here and show me what the int pointer memory looks like. Ooh, that's kind of fun, right? You can say, hey, show me what it looks like. These locations here are the memory locations. They are in hexadecimal. All this nonsense is also in hexadecimal. I think we better take a little bit of a detour into hex land. Right? Because we need to know what this stuff means before we actually go and dig in. OK. Hexadecimal is what base? 16. Right? Let's see. First things first. These are hex numbers. These are also hex numbers. Each hex digit, okay, is actually 16 bits long. Or sorry, each hex digit is 16. This is 1 byte. I said this wrong. I must have said this wrong. Each hex digit is like enough for 1 digit here, but this total thing is 1 byte. So that's 8. Let's see, that's 1 byte. So it's each one of these is 16 bits long. Okay? So 16 bits, 16 bits, 16 bits, 16 bits. It's 1 byte, 2 byte. No, I lied. Each one is 8 bytes. 8, 8, 8, 8. I don't know, that's wrong. 8, 8, 8, 8. Okay? So you've got each one of these is, so this is 1 integer's worth. We'll get to the details of that in a sec. Okay? 16 squared is 256 bits, which is 1 byte's worth. Okay? 250, no. I lied, that's 4 bytes worth. Yeah, I'm wrong. Sorry, pay no attention to that. But the point of hex is that it's very compact. And let me show you how you actually go from decimal to hex. Let me show you how you go from that, OK? All right. Each hex digit, OK, 0 through 9, and then because you've got a base 16, you better do 6 extra digits, OK? A, B, C, D, E, F are the 6 extra digits. They're not really digits, but they're in the place of digits because we don't have any other actual digits, right? Here's the decimal equivalents. 0 through 9 are the same, and then A is equal to 10, B is 11, 12, 13, 14, 15. OK? All right. So converting from decimal to hex is actually pretty straightforward. Just divide by 16, and what you end up doing is the remainder is your least significant digit. In other words, the one that counts the least in this. And then the quotient that you get, the integer quotient, is what you divide again by 16, and you keep repeating. Let me show you an example. Okay? Let me show you an example. 2,913 in decimal. Divide it by 16. What do you get? You get 182 with a remainder of 1. That means the 1 is the last digit of your answer. Then because you got 11, because you got 182, you do 182 divided by 16, and you get 11. And that gives you a remainder of 6. 6 is your second most digit. And then you do your 11th left over, so you do 11 by 16. You get 0 with 11 remainder. 11 is your next digit. Well, there is no 11 digit, but it's B. Right? B is 11. So you then have B61. Now you've got 0 left, and you're done. So B61 in hexadecimal is equal to 2,913 in decimal. OK? Yes? Actually, yeah, that's a good question. Memory locations are, it depends on the memory system you're using. Sometimes they truncate it because all above is not really used. So it's generally 32 bits or 64 bits or 48 bits or somewhere in the middle. But they generally truncate it to a number that fits on a table like that. OK, so let me do another example. 43,981. Decimal to hexadecimal. Divide by 16. Get the remainder. 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 The remainders are 13, 12, 11, 10, which are D, C, B, A. So that means that D, C, B, A is the way the hexadecimal comes out. So the number A, B, C, D is actually 43,981 in decimal. Who knew? Right? And you can go back and check this if you want more details on it. All right. Going the other way is not too bad either. It's actually exactly like you would think of getting the total for a decimal digit, except now instead of multiplying by tens columns, you're multiplying by 16s columns. So D, A, B, C, D in hex. D times 16 to the 0. That's the 0th column, the 16 to the 0th column. C is 16 to the first. B is 16 to the second. A is 16 to the third. 16, D times 16 to the 0th. 13 times 1 is 13. C times 16 to the 1. C is 12. 12 times 16 is 192. B is 11. B times 256 is 2816. And A, which is 10, times 4,096 is 40,960. Add all those together, and you get back to the 43,981. And I wish I could say numbers today. 43,981. I'm losing it. OK? So that's how you go backwards. It's fairly straightforward. OK. Let's get back to our memory here. Remember, integers are 4 bytes. So 1 byte, so each hex, let me go back to what I said before so I clear it up. Each hex digit is, has 16 positions, right, which is 2 to the 4th. So it's 4 bits each. So this is 8 bits. 1 byte is this guy. OK? 1 byte, 2 bytes, 3 bytes, 4 bytes. That makes up an entire integer. OK? So your integer in memory looks like this. There's one integer. If you do int pointer plus 1, that's the second integer. If you do int pointer plus 2, that's the third integer. See how that works? The compiler knows that. The compiler says go by 4s because the integers are 4 bytes, and compilers and memory systems count by bytes at a time. OK, we get that idea? First one, second one, third one, by 4s. Yeah, Allie?
So what is the 0A00?
We'll get to that.
Okay.
Good question. What is a 0A business? Let's get to that. Do you remember what the number for A was?
11.
10.
Close. It's 10. And remember what we were putting in here? This is what we had put in the thing before. We put 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. So that's going to be 10. What do you think that is? 20, 30, 40. If you do the calculations, you'll find out that the hexadecimal number for 30 is 1e. Hexadecimal for 20 is 14. How do we know? Well, 4 times 1 is 4. 1 times 16 is 16. What's 16 plus 4? 20. So that's got to be 20. OK? It looks backwards, though. Doesn't it look backwards? Because it goes, if this is our whole digit, why is the 14 on this side? Oh, that's a really good question. Okay. What number are we currently looking at? Sorry, it's tough to read up there, isn't it? We have to take all 4 bytes. Okay? We spent a bunch of time on this morning about this, and it's kind of a confusing thing. Computer systems, when this is actually based on just a decision they made, depends on the computer you're using. If you have 4 bytes like this, 1, 2, 3, 4, what do we normally think the lowest memory location is? This one, right? So we'll say that's the 0th one, 1, 2, 3. And that's actually how this is done up here. This is like memory location 1002003A10, and this is 11, and this is 12, and this is 13, etc. OK, makes sense? All right. What the computer does is it says, OK, I'm going to store my numbers such that the least significant byte is lowest in memory. It kind of almost makes sense. If you're storing the lowest one in memory is the least significant one. The higher one in memory is the most significant one. So for our 10 up here, 0, 0, 0, 0, 0, 0, 0, A. A is our 10, right? The rest of this digit is all zeros because we are dealing with a very small integer of only 10. But what it does is it says, this one is the least significant one. It doesn't matter as much as the higher ones. You're talking about did I ever tell you my favorite joke about my favorite nerdy science joke? It's about significant digits. You guys remember significant digits from like science class? Yeah. So these 2 guys walk into a natural history museum. They go to like the science museum or something. And one of the guys says, hey, see that dinosaur over there? That dinosaur is 1,000,004 years old. And the other guy goes, how do you know the dinosaur is 1,000,004 years old? And the first guy goes, well, I was here 4 years ago, and they told me it was 1,000,000 years old. Right? It's because the 4 doesn't matter. It's the least significant part, right? The least significant part is the last digit of a number. And so the last digit, what they're saying is put the last digit first in memory, 0A. So then you go higher in memory, you get the next significant digit, 0, 0. And then the next one, 0, 0, and the next one, 0, 0. That's how this is represented. So this is 10 because it goes 0, 0, 0, 0, 0, 0, 0, A. It took until somebody in earlier class named Allison pointed out, she goes, wait a minute. You're telling me that you read these numbers bytes right to left, but you read each individual byte itself left to right. And I went, oh, you're right. You do, actually. This byte is going to be 0A, and in memory, it's going to be the bits associated with 0A, and then the next, and in the order you think it is, right, from lowest memory to highest memory. It's not really memory at that point. There's kind of, that's the byte. But you read it like this. You go, OK, read it 1 byte at a time for 4 bytes backwards, byte, 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 but then put it like this, 0, 0, 0, 0A. 0, 0, 0, 0, A. You don't flip it like that. You don't read it totally backwards. Weird. This is called little endian format, okay? Where the little end of the number, in other words, the least significant byte, is the one they put lowest in memory. Other computers do the exact opposite. Why? Because they design it that way, and it doesn't actually matter. Nobody really cares. Okay? Networks are big endian. In other words, networks would send, if you're going to send this number, networks would send this one, then this one, then this one, then this one. And if you do it wrong, where you're just like grabbing memory wrong, you'll end up putting it backwards in memory, and every byte will be flipped the wrong way, and it's ugly. So you got to know that. You had a question, Jason?
I'm going to ask why you need a byte to store 2-digit text decimal.
Oh, now you do need 1 byte to, right, because it's 4 bits each character, each digit, right? I kind of screwed that up earlier. Okay. All right. So do we see how the memory works now? It's kind of interesting. Okay. The memory work. This is next memory location up like this, but then bytes or integers are stored little endian. The little end first. Yeah.
Are the memory locations of each one of those 3 different integers all the same? Or they all look like first?
Okay. Careful with your question. Are the memory locations of each individual, like each integer, the same? Yes, because ints are 4 digits long. So for instance, the memory location of this integer is 100203A10. The memory location of this integer is 100203A34 for this integer, right? But integers take 4 bytes, which means the first integer in here, the first byte, is at this location. This byte is at 3.5. This byte is at 3.6. This byte is at 3.7. Right? Now, when you add 1 to a pointer, it says, oh, I know it's 4. I'm going to jump from this location to this location. That's how it does it. Okay. All right. So let's see. So we've got this one 0014, so it's written this way. Oh boy, that is crazy. Okay. Let's see. Oh yeah, I already talked about this. 14000. It is 20. We did that already. Third integer is int pointer plus 2, the first, the second, the third. And it picks it out. And when it prints it out, it needs to know the bytes of this. You will get very, very good at byte notation in Comp 40. You'll get very good at it because you'll do it all like every day. Okay? Don't let it scare you. You can also, like we're going to do another one here. So I'm going to put one fun thing about hexadecimal. You can actually spell out some letters, right? If they use A, B, C, D, E. Microsoft is actually famous for putting 0x, which just means hexadecimal, D, E, A, D, B, E, E, F, into some of their code. And what it's there for, it's just, if you look at some parts of their like memory, it just says dead beef, dead beef, dead beef, dead beef, dead beef, right? And you're like, what are they doing? Well, they initialized it to say this so that when some programmer who is debugging it looks at the memory, they can say, oh, that's not initial, or that's been initialized already. Right? And they initialize it to this so that they can pick it out. So it's easy for humans to pick it out, but kind of funny. It's normally just for debugging. Let's say that we put at int pointer plus 8, we put 0xBEEF. Okay, well, that would be here, and it would be 00BEEF. Right? You see why that's the case? Because EF is the least significant digit. BE is the next least. You've got 8 bytes total, and that was 1 byte, 2 bytes. Or sorry, you've got 4 bytes total. 1 byte, 2 byte, 3 bytes, and 4 bytes are the other zeros. Highest byte, next highest byte, next highest byte, last byte. 00BEEF. Interesting, huh? And then at 9, if we did A, B, C, D, E, F, 0, 1, A, B, C, D, E, F, 0, 1. See how that works? Kind of neat, yeah.
And if you don't put the 0x before like what is it?
It would say, I don't know what you're talking about. It would think it was a string or some other text. It would not know. It knows that it's 0. It knows that it's BEEF because it's the 0x. It knows that it's a hexadecimal number.
And what if you didn't put the 0x and then put like a bunch of integers? Would it just assume it's base 10, or would it?
It would assume it's base 10. The one time it doesn't is if you put a 0 in front of it, it will think it's an octal number, which is base 8, which is another number system we can use. But we're not going to worry about base 8 today. You might do it in Comp 40, but I don't think you'll spend much time on it. But base 8 is, some people got into trouble, found they had bugs in their, they thought they had bugs in their event code or whatever for converting 24-hour time because they were trying to put 0900 for 9 a.m. And the 0 would say, oh, it's an octal number, change things around. And it got all confusing. But we fixed that on Piazza. But anyway, the point is, you do use the 0x to call something a hexadecimal number. Okay? All right. So, okay, we've done hex now. And you've actually seen, this is going to be really important getting your head wrapped around that. But we've seen hex. There's also, of course, binary. Right? Binary is, at the lowest level, what the switches are in your computer. Right? Computers are based on binary. Right? Binary is not the most easy to use number system because numbers get so huge. Right? You will have to do bitwise calculations. What do I mean by bitwise calculations? I mean something like this. 1101 or with 0110, right? Each bit gets ORed with the other bit. So 1, 0 gives you a 1, 1, 1 gives you a 1, 0, 1 gives you a 1, 1, 0 gives you a 1. So 1, 0, 1, 1 ORed with 0, 1, 1, 0 gives you 1, 1, 1, 1. That is different than a logical OR, which is the ones we generally use. How do you do this? If you have two numbers, one is A and two ints, A and B, and you do A or B with only one of those instead of two, that will give you a bitwise OR, not a logical OR. And that will return a value that's the ORed values bitwise of these two things. Okay, that's some novice programmers all do this and they get it wrong, right? Same thing goes for A ampersand B would be in bitwise and of those two numbers. Okay, you'll do lots and lots of bitwise stuff, and you'll learn it too in Comp 40. But just wanted to show you that you're going to need to be able to do that. Okay, converting decimal to binary, same process as doing decimal to hex. Instead of dividing by 16, divide by 2. So you divide the number by 2, and you say 23 divided by 2 is 11 with a remainder of 1. What's the remainder always going to be when you're dividing by 2? Either 0 or 1. So 23 divided by 2 is a remainder of 1. 11 divided by 2 is a remainder of 1. 5 divided by 2, remainder of 1. 2 divided by 2, remainder of 0. 1 divided by 2, remainder of 1. And you read it backwards. 1, 0, 1, 1, 1. 1, 0, 1, 1, 1 is your binary number for 23. That's nice, right? And you're done. Pretty easy to do. Notice 23 went from 2 digits to 5 digits. That's not so good, because it's kind of ugly. Don't get me started on base 1. Base 1 is just ones. So 1 is 1, 1, and 2 is 2 ones, and 3 is 3 ones, and a million is a million ones. Don't want to count in that one either. To go backwards, same thing. It's just powers of 2, right? It's going to be, in this case, it's going to be 1 times 2 to the 4th, because this is the 2 to the 4th column. 0 times 2 to the 3rd, 1 times 2 to the 2nd, 2 to the 1st, 2 to the 0th. Add them all together, and you get back to 23. Okay, you can do this on your own if you want to check it out. But it's just straightforward conversions like you might do in math class. Okay. As I said, these numbers get really big. 5 million in decimal is this number in binary, right? You don't want to deal with these numbers every day. They're too darn big, right? Well, you also don't really want to deal with them in decimal, because decimals and base 2, they don't mix very well. What does mix very well, however, is hexadecimal and base 2. Well, it turns out because base 2 is 2, hexadecimal is base 16, which is 2 to the 4th. It's actually very, very easy to convert back and forth from hex to binary. You've got all your hex digits here. This is what they convert to in binary. Notice something. You get 4 digits each chunk. Each hex digit is 4 bits long. That's what I was getting at earlier, right? Each hex digit is 4 bits. And therefore, if you need to convert this to hex, chunk it into 4s, 4, 4, 4, 4, 4, 4. And look at this. 0, 1, 0, 0 happens to be 4. 1, 1, 0, 0 happens to be C, right? 1, 1, 0, 0. 0, 1, 0, 0, another 4. 1, 0, 1, 1 is B. 0, 1, 0, 0 is another 4. And 0, 0, 0, 0 is 0. 4C, 4B, 4, 0. This entire number gets crunched down to 1, 2, 3, 4, 5, 6 digits long. And you can go back and forth really easily. None of this dividing business. Just, hey, what's the hex digit for 4? Oh, it's 0, 1, 0, 0. There's your first digit. Pretty nice, huh? Okay, so that's one of the big reasons we use hexadecimal, because it's compact and it translates to binary very, very easily. Okay? All right, so that's about it for the Comp 40 rundown. Lots of references. This is the one you need to go to if you're going to take the class next semester. Go get up to speed on that. You'll make yourself and your professor very happy next semester. I hope that was helpful for those of you guys who are doing it. Questions on that? Questions on Comp 40 in general, the project, anything else? Yes?
Do you know who is teaching the class next semester?
Yes, it's going to be Professor Noah Mendelson, who taught it this semester. And he's great. Yeah, you'll have a really good time. He's a super smart guy. He knows all the important people in computing over the last 50 years. He knows them all personally. It's kind of cool. Yeah, and he's really smart. Okay. Other questions? All right. See you guys Monday.